Hello students, welcome back. Previously we completed section 1 of this notebook except for theorem 1.5. The reason I skipped this, and the biggest reason I skipped this in skipping now is the difficulty. This is theoretically difficult. It's not really long and tedious computation. The computation itself is manageable, but theoretically it is a little bit difficult. So we're going to do that when we do section 4 of this notebook. Otherwise, here's a quick review. We define the determinants for 1 by 1 matrix, which are just real numbers, and 2 by 2 matrices given by this crisscross AD minus BC. And then one of the application was the inverse matrix formula for 2 by 2 matrices, and the proofs straightforward and simple. And then we did the properties of the determinants, 3 fundamental properties of the determinants: bilinear, alternating, and identity. And bilinear, what do you mean by bilinear? 2 linearities put together: linear with respect to the first variable, linear with respect to the second variable. Alternating, switch 2 column vectors, we get negative, and then immediate consequences, nothing to change, then 0. And the determinant of identity is always 1. Proof was simple. Now let's establish something similar to matrices of order 3, or 3 by 3 matrices. Oh, actually before that, let's go over determinants of order 1. Okay, 1 by 1 matrices are just real numbers, and all real number arithmetic rules apply, and here are some lists of those real number arithmetic rules. Simple. Okay, determinants of 1 by 1 matrices, just themselves. Therefore, it's linear. Duh. Preserved multiplication, again, duh. Determines invertibility. Oh yes, we have to have the fraction 1 over a, so denominator should not be 0. That makes sense. And then the uniqueness, even though this computation is not difficult, theoretically uniqueness thing is a little bit difficult concept, so let's just move on. And that was a quick review of the concepts that we are going to review. The review of concepts that we went through for determinants of order 2 in the viewpoint of determinants of order 1. So my purpose was to review those concepts, not the techniques. And not coincidentally, we're going to go over through the same concepts again for the determinants of order 3. Here we go. First, the definition. And the definition, oh my, more complicated matrix, more complicated determinant. But then again, there is a rule similar to this crisscross rule. Yes, principal diagonal plus the other diagonal minus. We have something similar going on here. Principal diagonal, a times e times I, that's positive. But then again, there are other numbers. That is b times f times g, because we ran out, so we continue over here, that's reproduced over there, bfg, and then keep going on to the principal direction, c times d times h over here. Those are plus. Now the other diagonals, c times e times g, that's clear. And how about these two numbers, fh? We need the extension here, a times f times h. And then how about this one? Well, cover this b times d and I. Those are negative. And add them all up with appropriate signs, and that's a determinant. Now, if you somehow end up with 4 numbers multiplied, something is wrong. something like b times f times d times h, you didn't do it right. Each time you're going to get 3 numbers multiplied in each direction, pluses and minuses. An example problem is in order, so let's go ahead and do that. Oh, by the way, this is 2 by 2, no problem there. How about this example? All right, here's one method, and that's by the direct definition. Negative 2 times 0 times 3/2, that's straight ahead computation is 0. That's easy, okay. Next, 4/3 times negative 1/2, negative 1, excuse me, 4/3 times negative 1 times this number times 2, and there is a second multiplication. Let's keep going on in principal diagonal direction. 1 times, and then 1 times 1/3. 1, 1, 1/3. You have to have 3 numbers, all right? 1 times, and then 2, and then if you run out, that's wrong. If you have 4/3, negative 1 times 1 times 1/3, that's not right. You have to have 3 numbers. Okay, let's go the other direction. 1 times 0 times 2, oh, that's easy. That's 0. And how about these? 4/3 times 1 times 3/2. Okay. And then negative 2, and that direction, times negative 1, 1/3 over there, and then calculate them all, you're going to get negative 5. It's basically this exercise. We just repeat it with these numbers. I assign similar homework problems as well, so do once more and then you're going to get used to this very quickly. Alright, that was the definition, and then let us go over to the next topic, the basic properties of determinants, which corresponds to these basic properties of determinants: bilinear, alternating, and identity for order 3. So we have trilinear, because we are talking about now 3 column vectors, so we need 3 linearities put together. Linear with respect to the first variable, do you see it? Second variable and third variable, those are kept the same. A2, A3, A2, A3, they're kept the same. With respect to the first variable, this linear combination of ax plus by is separated nicely, as you can see in the right hand side. Similarly, linear with respect to the second variable. Third, linear to the third variable. So 3 linearities put together, we call it trilinear. These are all examples of multilinear. Next, alternating. Switch 2 column vectors, then we have negative. We can switch x and y and z, and then z and x. Is there any other? No, there are only 3 columns, so there are only 3 switchings. And by the way, here is the immediate consequence. Switching first and second column, we can switch those, but then again, even after switching, there's no change because those 2 columns are identical. So we have to have the same result even after taking the negative value. What real number stay the same after taking the negative? Only 0. So we have these properties which are immediate consequences of alternating properties. 2 identical columns, immediately 0. And finally one more, identity. Well, as a matter of fact, this one you can prove it directly. I mean, determinant of okay, so that's determinant of the identity matrix, and then you can apply this definition or this practical method. Let's see, multiply the principal diagonal, 1 times 1 times 1, okay. Next, we multiply 0 times 0 times 0, so that's 0. And then we have 0 times 0 times 0, so that 2 is 0, minus the other diagonal, 0 times 1 times 0, that's 0. And then we have 0 times 1, that 2 is 0. And 1 times 0 times 0. So we have 1, a trivial computation. So we have all these properties here. We proved the identity property, but trilinearity and alternating properties we didn't prove yet. We're going to prove those in section 3 along with the arbitrary order. Next property, further properties of determinants, and then how about the determinants of transpose matrix? That's not going to be too difficult if you really want to prove it, because all you have to do is to go back to this definition and take the transpose. This is going to be a little bit confusing. So from here, take the transpose, which is switch D and B, switch C and G, and switch F and H and so on. Yeah, those three. And then do the determinant computation and see if it's the same as the original. It's going to be a brute force computation, tedious but not difficult. Speaking of tedious but not difficult, here's the culmination of it. You'll have to do the matrix multiplication for 2 3x3 matrices, all symbolic, A, B, C, D, E, F, G, H, I, and then you may even, okay, there are another 9 numbers, so there are 18. Okay, you're not going to run out of alphabet, but still, come on. And then determinants of first, determinants of the other, and then follow those out. Good luck. Nothing is difficult, but extremely tedious, but it'll turn out okay in the end. Next, determinant of inverse matrix, 1 over determinant of the original. As a matter of fact, this is not too bad. If we prove this, then determinant of A inverse times A is going to be determinant of identity, so it'll turn out okay. I think I gave you a bit too much hint already. Now let's go to the final topic here, that is reducing the determinant of order 3 into determinant order 2 by this formula. So determinant of order 3 can be reduced a summation of 3 determinants of order 2. And consequently, if you can calculate the determinant of order 2, then you can calculate the determinant of order 3 as well. Of course, is this more effective than this definition? The answer is generally no, but this is big but. This idea is the fundamental idea that you're going to employ for determinants of arbitrary order. For example, how do you calculate the determinant of order 5? Use similar idea to reduce into 5 determinants of order 4. And then each of those determinants of order 4, you reduce to 4 determinants of order 3. So 5 times 4, we have 20 determinants of order 3 to calculate. And those kind of things are the fundamental idea behind section 3 and section 4. So this exercise is by itself not big, but as a preparation for what's to come, it's an extremely important exercise. Okay, enough introduction, let's begin. So we have first row A11, A12, A13, there are 3 numbers, and those 3 numbers A11, A12, and A13, they come. And how do we select these determinants? They're called, this is called deleted matrix because from A11, we selected A11, right? From A11, we delete the rows and columns where this A11 came from. So first row, first column, those are deleted. What's left is this deleted matrix, and that determinant we calculate. Next, we have A12, second number. So this A12, and then we delete the row and column where this A12 came from. So first row, second column, they are gone, and what's left is this deleted matrix. and that determinant we'll calculate. And then third, A13, so first row, third column are gone, and what's left is this deleted matrix. Let's have one exercise. No, not yet. It turns out this is not the only way to do it, because as you can see there, oh, excuse me, I didn't complete this method. Sorry about that. I explained 99%, but I missed that 1%. Okay, let's go back. First row, and these numbers, A12, A11, A12, A13, and deleted matrices, all done. Now, 1% that I didn't complete is a sign. We have alternating sign, plus, minus, plus. Always like that. We have to have alternating sign. And that is a big reason why we are having that alternating property. Okay, now let's go to the second row. There are 3 rows, so we use the first row. What if I use the second row? Similar. A21, A22, A23, those are 3 numbers. And we take the deleted matrices. So we want A21, and we delete the row and column where this A21 came from. So second row, first column, gone, and what's left is this deleted matrix, and we calculate its derivative. Do the same thing here. A22 came from here, so second row, second column, gone. What's left is this deleted matrix, and finally A23, excuse me, so second row, third column, gone, and what's left is this deleted matrix. That covers 99%. What's the remaining 1%? Signs, pluses and minuses. Instead of plus, minus, plus, this time we have minus, plus, minus. Why? Because we start from plus here, and each time I move, I have sign change. So I have here plus, minus, plus, that was here, but this time, this is plus, and then we come down, minus. And then we have minus, plus, minus, that's what you're looking at. So either way, each time I move, either horizontally or vertically, we have sign change. Plus, minus, kind of like that. Now if I use the third row, please note that this is plus, minus, plus, because we begin with plus. Next we have minus, minus, and then plus. So we start from plus. Here's a summary. You see, alternating signs. Not only that, we can do the same thing to columns as well. You see, instead of first row, I can use first column, A11, A21, A31, plus, minus, plus, and then the usual deleted matrices. Remove first and second, first row and first column, and first column and second row, and so on and so forth. And for this one, plus, we have minus, plus, minus. So we have minus, plus, minus with all of those deleted matrices. So keep those in your mind, and let's have an exercise. We already did this problem using the crisscross method, and the answer was -5. And then can we use the same thing using the second row? We have, this is plus, so we have minus, plus, minus, so we have minus, plus, minus, and then we have 1, 0, -1, 1, 0, -1, and then the deleted matrices. And if we do your computation correctly, you're supposed to get -5, and the detailed computation, which is not difficult but tedious, is left to the students. Look at this. I selected second row because 0 makes my computation easier. We always begin with plus here, so minus, plus, minus with these numbers with deleted matrices.